Hi, so if you are starting out in Chemistry 2, then you are going to be hit with kinetics and the reaction rate, how to find out the reaction rate. And that's one of the first things you study in Chem 2 usually. So this is a breakdown so you can understand it simply and do the problems easily. A reaction rate, if you want to understand a reaction rate, you just have to understand what a rate is. A rate is just the change in the amount. So the change is going to be the final minus the initial over the change in the time. So that's going to be the final time minus the initial time. So a good example of this is if you drive 60 miles, say you left at 5 p.m. and you got there at 6 p.m. So the final minus the initial time equals 1 hour. So that's going to mean your rate of speed is 60 miles an hour. So that's also called speed. But speed is just a form of a rate. Now the reaction rate is what we want to actually focus on here. And the reaction rate is the rate of the reactants in a chemical formula changing their concentration. They're getting all used up. So if you have, say you'd have, just chemical A, and that yields different products. Chemical A, or molecule A, is going to be the reactant. And as the molecule A breaks down into these products, the concentration of A is going to decline. So if you start out with 10 molarity of molecule A, but then you break it down into some products, then after a certain period of time, you might only have 5 moles of A left because the other 5 moles of A has been used up and broken down into the products. So the reaction rate is just the speed at which A, the reactant, breaks down and forms the products. So as you can see here, it's the change in the concentration, which is final minus initial, and the concentration is usually designated by these little brackets here that I put around A. And concentration, let's see, concentration is usually in chemistry defined as molarity, which is capital M. So, but we just put the brackets around it so you understand we're talking about the molarity or the concentration of this reactant. So the change in the concentration, from our example, the 10 moles or the 10 molarity turning into 5 moles or 5 molarity because the other 5 went off and became products. So the change in concentration in this example would be 5, and that's 5 molarity, but we're just going to put 5 with brackets around it. And then over the change in time, the final minus initial. So if you started with a stopwatch and you started at 0 seconds and you stopped at 10 seconds, that's the final minus the initial. That's going to be 10 seconds. So this rate of reaction is going to be 5, the concentration of 5 over 10 seconds. And that's going to be the rate of reaction. Now the reaction order, this is a really important idea to grasp. It does not mean the order, like chronological order, like 1, 2, 3, 4, etc. The order it's talking about is how the rate depends on the concentration of the reactant. So the rate is affected by how concentrated that molecule is. In our previous example, it was molecule A. And so the rate is going to depend on if we started out with a concentration of 10 moles of molecule A, or if we started out with a concentration of 10,000 moles of molecule A. That's all going to affect the rate. And there are three basic orders that you're going to need to know for beginning Chem 2. There's more than this, but you don't need to worry about that for Chem 2. That's in more advanced chemistry classes. But there's three basic orders. There's the zero order, and in the zero order, the rate actually is not affected by the concentration. It's independent of the concentration. So it doesn't matter if it would be 10 moles of A or 10,000 moles of A. The rate is going to be the same. The rate is completely independent from the concentration. Then we have something called the first order. And you'll see how we can figure out what is zero order, first order, and second order in a minute. But in the first order, the rate is proportional, directly proportional to the concentration. So if we've started out with 10 moles of molecule A, so I'll put in here brackets 10, then the rate is going to be something, I don't know, I'll just say 1. But if we start out with 20 of molecule A, the rate could be 2. So see, the rate is affected. It goes up as the concentration goes up. So it's directly proportional to the concentration. Then we have the second order. And the second order is like the first order. The rate is proportional to the concentration. But if we start out with 10 moles of A and we move to 20 moles of A, and the 10 moles of A means the rate is 1 second, the 20 moles of A is not going to be 2 seconds, it's going to be 2 squared seconds, which equals 4 seconds. And I'll show you a little bit more about that here in a minute. But see, the second order rate is going to be proportional to the square of the concentration. Now, how do we determine the order of a reaction? And remember, this order does not mean chronological order. I think I say it right here. Does not mean chronological order, like 1, 2, or 3. The order is just numerically labeling different ways the rate is affected by the concentration of the reactant. Now, this can only be determined experimentally. You have to do these experiments and see how the numbers play out. And the experiment that we use to determine the order of the reaction is called the method of initial rates experiment. And the method of initial rates experiment means you do different experiments. So here's your experiment 1, experiment 2, experiment 3. And then here is going to be the concentration of A. So in experiment 1, our concentration of A was 10. But in experiment 2, we decided to use the concentration of 20 moles of A. And experiment 3, we used the concentration of 40 moles of A, of molecule A, of the reactant A. And then the initial rate is the time the reaction begins. The time the reaction begins. So if we take A and we turn it into products, we break it down into products, once that reaction starts happening and the A starts turning into products, then we time it with a stopwatch or whatever timing device you have, and let's say this first concentration of 10 A takes 1 second before the reaction begins. Then this concentration of 20 moles of A is going to take, I'll just say 2 seconds, and I'm just making up these numbers. And then the concentration of 40 moles of A could take 4 seconds. And again, I'm just making up these numbers just so you can get an idea of the fact that these are 3 different experiments with 3 different amounts of concentration. And then we time it to see how long it takes for the reaction to start. So, as I said, the method of initial rates experiment is when you take the initial rate, which is at the beginning of a reaction, when the reaction starts, and it's measured at different concentrations of the reactant. And remember, the reactant is the molecule on the left side of the yield arrow. So if you have A and then you yield some products, the reactant would be the A. So then once we have that information, we look at the increase in the initial rates compared to the difference in their concentrations. Just like I had on the chart that I had just did on the previous slide, those concentrations went from 10, and then we did an experiment where the concentration was 20, and we did an experiment where the concentration was 40. And you look at those initial rates, how long it took for the reaction to start happening, and you compare those, and I'll show you how to compare those. Now in this one, we took a concentration of a reactant and I put in molarity, just to remind you, but instead of in molarity, we just usually put brackets around it, like we would put brackets around A, and that would denote that we're talking about the concentration of A. So in this chart, in these experiments, this is experiment 1, experiment 2, and experiment 3. In the first experiment, we used 0.10 molarity of A. In the second experiment, we used 0.20 molarity of A. And in the third experiment, we used 0.40 molarity of A. And now look over here at the initial rates. This is the time in seconds that it took before the reaction started happening. Now if you look at these initial rates, these are all the same. So it did not change. It took just as long for the reaction to take place when we used concentration of 0.10 A, and it took the same amount of time if we started out using the concentration of 0.2. It took the same amount of time if we started using the concentration of 0.4. Now between the 0.10 and the 0.20, this is a doubling. We doubled the concentration, right? And from 0.20 to 0.40, we doubled it again. But even though we doubled the concentrations each experiment, the initial rates stayed the same. 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 So no change. Another way to put no change is to call that 0. 0. So when you have doubled the concentration, we're going to put a 2 down for doubling the concentration, but then we have no change, 0. We're going to use that 0 as an exponent. And we can also write that with the concentration of A. Remember those brackets mean concentration. And then we just put the 0 up at the exponent outside of the brackets. Now, any number raised to the 0 power is going to be 1. Not 1A, not the concentration of 1, just 1. If you have 14,342 to the 0 power, that's going to equal 1. If you have 2 to the 0 power, that's going to equal 1. So if you have a concentration of A to the 0 power, and remember the 0 came from no change, that's going to equal 1. So since this exponent that we're putting up here, because of no change, the 0, that means this is going to be 0 order. And I'll just put a line through it so you know it's a 0. So this is going to be a 0 order initial rates experiment showing that this concentration or this reactant is of the 0 order nature. Now let's look at another one. This is a new one, and this is again the concentration of A in moles. So that's these, and we have experiment 1, experiment 2, and experiment 3. Now if we compare experiment 1, the concentration of experiment 1 to the concentration of experiment 2, this doubled. Okay? And also we can do the same thing over here from 0.20 to 0.40, that doubled. So we're going to write a 2 down here because it doubled. Now then we're going to look over at the initial rates. We went from 0.015 to 0.030. So this doubled. And we went from 0.030 to 0.060. So that also doubled. So as you can see, as we double the concentration, we double the amount of time it takes for the reaction to take place. And same down here, we doubled the concentration, and that doubled the time it took for the reaction to start taking place. So if we have this 2 down here for doubling the concentration, and the initial rate is also doubled, then we want to put some exponent up here that's going to give us 2 for doubling. It's going to give us the answer 2. So what exponent belongs up there after the 2? That's a 1. So 2 to the 1 power is 2. So this 1 power right here is how we're going to know that this is first order. So this is going to be the first order. So every time the concentration is increased, the initial rate is increased at the same pace. So first order means the rate is directly proportional to the concentration. Now, one more time, remember this is going to be the concentration of A in molarity in this column. This is experiment 1, experiment 2, and experiment 3. And this concentration went from 0.10 to 0.20, so that doubled. And let's look over here at the initial rate. It went from 0.015 to 0.060, so that quadrupled. And let's look down here to make sure that we're doing this right. Let's do another one. We'll start with experiment 2, and the concentration is 0.20, and then we went to experiment 3 to the concentration of 0.40. So that is doubled also. And let's look over here. We go from experiment 2 to the initial rate is 0.060 seconds. And as we doubled the concentration, the initial rate quadrupled, because 0.060 times 4 is 0.240. So it quadrupled, it times 4. So if we go back to the fact that we had doubled this in the concentration of the reactant, and we're going to put a 2 there. But the initial rate, as we increase the concentration, quadruples. We need to find out what exponent we should write right here to make this math problem correct. And the answer is 2. If you take 2 squared, you're going to equal 4. So since this exponent has to be 2, that means it's going to be second order. And just like the first order is directly proportional to the concentration, the second order is not directly proportional, it's exponentially proportional. So that means it's going to be squared. And we're just going to write the A in brackets, the concentration of A in brackets, which is this first column right here. And then we're going to put the 2 for the second order as the exponent outside of the brackets, and that is second order.